I'm going to go over two different sample calculations for rotational dynamics. The first one is similar to the types of things that you'll be doing on your homework. The second one is probably a bit more complicated. It might be something that's on a bonus problem. So you don't need to take so many copious notes on that one, but you might want to skim over it to see how that type of problem works out. Alright, the first one, you have a globe in your room and you decide to do a little physics experiment with it, so you spin it up as fast as you can and time how long it takes to stop. From that information you can now calculate a few things. Yes, you are a certified Davidson Academy nerd, but that's okay. We want to find the angular acceleration, so this is kinematics that we're dealing with first here, rotational kinematics, and we like to start out by listing everything we know. We know the time here is 7.4 seconds. We've got this 85 RPM. Now that is not our rotational velocity, that is our frequency. So we're going to use that to convert to our initial rotational velocity. Remember, the relationship is 2 pi times the frequency. So we can do 2 pi times 85. Now that 85 was revolutions per minute, and we want to convert to radians per second. So we're also going to divide that by 60 to make it convert minutes to seconds. This gives us about 8.9 radians per second. Our final velocity we know is going to be 0, and then what we're looking for is the angular acceleration. So looking at these quantities here that we know, we now need to pick our kinematic equation, which is going to be omega equals omega naught plus alpha times time. And we just plug in our information. We've got 0 equals 8.9 plus alpha times 7.4. Alpha works out to be negative 8.9 over 7.4, which is negative 1.2 radians per second squared. We get a negative here because we called our initial velocity right here, we called that positive. And since we're slowing down, that means we're going to get a negative. We could have switched those, it doesn't really matter. Most of the time we're just concerned with the magnitude of these things. Now we want to know the torque stopping the globe. So the equation for torque in dynamics is torque equals I alpha. Now I, the rotational inertia, there's not one set formula for that, and that depends on the shape you have. In this case we have a hollow sphere. So what you'd want to do is go look up the moment of inertia for that shape. Often I'll probably just give it to you right in the problem and be like, oh, hollow sphere moment of inertia is this. But just in case I forget that sometimes, you can always go to this nice little sheet here. I'll probably print this off for you, so you don't worry about writing down all of these. Sorry if you did that earlier. So we come down here, we've got a sphere. Now this is a uniform sphere, which means it's a solid sphere. Oh, and look, conveniently, somebody put the formula for a hollow sphere on there. So 2/3 mr squared is what we need for that. So I is 2/3 mr squared. That whole thing is our moment of inertia. Then we multiply that guy by alpha. So now if we plug in our numbers, you also took the time to weigh your globe because obviously needed that information. The radius is up here, 15 centimeters. We want that in meters, so 0.15, and don't forget to square it. That whole thing is I, and then we multiply by alpha. I guess we can leave the negative in there. And the unrounded answer was more like 1.203, so we want to use more digits there. This works out to be a torque of negative 0.0217. We'll just, let's see, we got 2 sig figs, so 0.22 meter newtons are the units of torque. And we can check that those units work by looking at the units of what we plugged in here. So masses are measured in kilograms, the radius was meters, and we squared it. Alpha was radians per second squared. Radians don't really count, they're just a placeholder. So we have kilogram meters squared per second squared. Now if I separate out these meters squared and I pull one of them out front, I'm going to have meters times kilogram meters per second squared. This thing right here is the definition of a newton, so indeed it works out to be units of meter newtons. If you like checking units along the way, it can be a good way to see if you made a mistake, or if you're just really careful about always plugging things in standard units, then you can know that your answer came out with standard units as well. Okay, last one, we want the frictional force stopping the globe. So we're assuming you've got a rod going through the middle of your globe, and that is what it's spinning on, and that's where the friction is acting. So from a bird's eye view, if this is the rod and then you've got your globe, so not to scale here, the radius of this rod here, so the distance from here over there, is the 4 millimeters. So that's the distance from the axis of rotation at which the force is acting. So we can also use our equation, our other equation for torque, which is R times F. Now you also have to take into account the angle, but because these are concentric circles, the force is going to be acting perpendicular to the lever arm, or R. So you basically have sine of 90, which is just 1. So we can just do R times F in this situation. So we plug in that torque, negative 0.0, let's see, it was 217 before I rounded it a bit. R is going to be the 4 millimeters. Obviously we want that in, we want that in meters, so 0.004, and then we can just divide and solve for F, which works out to be a frictional force of 5.4, negative 5.4 newtons. Okay, so on to the next problem, which is a bit more difficult. We've got two blocks hanging from a pulley, so something like this. That's my pulley, here's my rope, magically not touching the pulley. And we have a larger block, 10 kilograms over here, and then a smaller 3 kilogram block. This is apparently a less dense material. So anyway, if we want to know the acceleration of these blocks, and we also have our pulley is 1 kilogram, and it has a radius of 20 centimeters, or 0.2 meters. And now we're going to take into account the rotational inertia of this pulley when we find the acceleration of the blocks. First of all, let's do a quick calculation ignoring the pulley like we would have done before, just to get a ballpark estimate of what the acceleration would be if this were a massless, frictionless pulley. And then we would imagine that if we take the inertia of the pulley into account, we should get something a bit less than the acceleration ignoring the pulley. So ignoring the pulley, we can just do F equals ma for the entire system. So on the system, you're going to have gravity on this guy minus gravity on that guy. Let's go ahead and call this block A and block B. So you'd have gravity on A minus gravity on B would equal the sum of the mass of the system, so mass of A plus mass of B. And we could solve for acceleration this way. So acceleration, this is going to be 10 minus 3, if you factor out a 9.8, divided by 10 plus 3. So the acceleration would work out to be approximately 5.28 meters per second squared. Okay, now if we want to factor in the pulley and the rotational inertia, we can't just use F equals ma because this thing is rotating. So how do we exactly factor in the mass of a rotating system? So we have to use torque equals I alpha, and we're going to use sum of the torques equals I alpha. And since this is a pulley, we're going to assume it's a disk. And the moment of inertia for a disk, if you don't remember, you can come back over here and say, okay, there's a disk, it's rotating about its center. So 1/2 mr squared is the moment of inertia of a disk. So we'll keep that over here, mr squared. Now the torque's acting on this disk. Be careful to not assume that it's just gravity on both of these. So I'm going to run through that real quick and show how ridiculous an answer you get. So if I say the sum of my torques is gravity on A minus gravity on B times the lever arm, R, and I set that equal to I alpha, where I is 1/2 m, I'm going to put mp for mass of pulley, times r squared times alpha. Now alpha is A over R, so we can go ahead and put that in, and kind of nicely this cancels one of those r's, that cancels the other. So we're going to get this expression here. But if I went ahead and plugged in these numbers, this is going to be 10 minus 3 times 9.8 equals 1/2 times the mass of the pulley, which is just 1, times acceleration. So you're going to have 7 times 9.8 times 2, and you get an acceleration of 137.2 meters per second squared, which is obviously ridiculous because this is much faster than the acceleration of free fall. So this is not how you want to do it. And you might suspect just by looking at this that we didn't really take into account the inertia of these two blocks, right? We considered the forces due to them, but we only took into account really the inertia of the pulley. And the reason why this is wrong is because if you think about the forces acting on this block here, you've got gravity down, gravity on A, and then you have some tension pulling back up, and that tension has got to be smaller than gravity, such that this block will accelerate downwards. And it's that tension that is, let's make our disk a little bigger here, it's that tension that's being exerted on the side of the disk. So our actual equation for torque needs to be the tension from A minus the tension from B. And these ropes are both equidistant from the center of that disk, so we can just multiply by the radius of the disk. That's our lever arm. So essentially this is the torque. Don't get confused with my T's and my tau's, sorry about that. So the torque from A is tension times the lever arm. Torque from B is tension times the lever arm. This is going to equal 1/2 mass of pulley times r squared. And we can go ahead and make that same substitution of A over R and make our R's go away. So that all works out nice. Now I don't know the tensions directly, so I can use force information to figure out equations for these tensions and then come back and plug them in. So I'm going to jump over here. For block A, you're going to have gravity on A, so we're just doing net force equals MA, right? Okay, so gravity on A minus the tension on A equals the mass of A times the acceleration. So if I solve this for tension on A, I'm going to get gravity on A minus its mass times its acceleration. And then we're going to do the same thing for block B. So on block B, just so that I have the same signs on my accelerations, I'm going to do the larger force minus the smaller force. And this one's accelerating upwards, so we're going to have tension on B minus gravity on B equals mass of B times the acceleration. These accelerations are going to be the same because this rope is not going to get loose. So we can assume that all these accelerations are the same. The acceleration of the blocks, acceleration of the rope, and the tangential acceleration of the disk, because it moves with the rope. We're assuming it's not sliding here. So that's why we can just leave one acceleration through all of these things. Alright, so solve this guy for tension on B. You're going to have mass of B acceleration plus gravity on B. Now I can plug all this in up here. So gravity on A minus mass of A times acceleration. That thing minus mass of B acceleration plus gravity on B. In parentheses, don't forget to distribute all that stuff. Okay, so this whole thing is equal to 1/2 mass of pulley times acceleration. Draw a line here just so we don't get confused. Alright, and this is really the physics of it. Now we just have to plug in numbers and we can solve for acceleration. If we want to factor some things out, we can. So I'm going to have gravity of A minus gravity of B when I distribute that. So that is going to be 10 minus 3 times 9.8. So those are my gravities. And then I'm going to have minus mass of A, I'm going to write it this way, plus mass of B times acceleration. So I'm just kind of collecting terms here. Equals 1/2 mass of pulley times acceleration. Now I've got another acceleration here, so I'm going to move this all over to that side. Might as well call this 7 times 9.8. This is going to end up being added, and then we can factor out an A again. So we're going to have mass of A plus mass of B plus 1/2 the mass of the pulley. So essentially we get what we had over here, right? We're going to have 7 times 9.8 divided by 13. Only we have to factor in the mass of the pulley, but it doesn't factor in completely. It's only half the mass of the pulley that factors in, so it's going to divide by something a little bit larger. The mass of the pulley is 1, so we're going to have 7 times 9.8 divided by 13.5, which is pretty close to what we had here, right? But dividing by a slightly larger number, which is going to make our acceleration slightly less, which is what we're expecting. 5.08 meters per second squared. There, we did it. Welcome to rotational mechanics. See you next time.